our white paper is Astrobiology on Mars, Organic Chemical Evolution on an Earth-like Planet. The green arrow there represents the timeline of organic chemistry or organic geochemistry research on Mars. It got off to a slow start more than 30 years ago with Viking, but in the last 5 to 10 years, there's been a series of quite significant discoveries of organic matter in Martian geologic materials, and we hope that these discoveries are the springboard that we were hoping for the next decade of Mars exploration that emphasizes further research and missions into understanding what's the composition of those organic materials. The pictures underneath are just an example of Mars geologic materials with organic matter in them. This is a Mars meteorite that contains what's being labeled as macromolecular carbon, which is essentially a skeleton of carbon atoms decorated with other elements such as hydrogen, oxygen, nitrogen, and sulfur. Remarkably, a similar type of organic material has been described in Bell Crater in sediments that are more than 3.5 billion years ago. And so these are the types of discoveries that recent discoveries that suggest that organic material might be present in Martian geologic materials, even if they're very old, and they might be widespread. And so with this white paper, we will recommend that the next decade of Mars exploration puts a priority on the research into the origin, distribution, and chemistry of organic matter in geologic materials on Mars. In our white paper, we will outline a series of questions and a detailed rationale for why we think this is a worthwhile focus of the Mars exploration program. Here, we just outlined a few of them. The fact that we find organic matter in these Martian materials suggests that organic chemical evolution is active on rocky planets. We cannot emphasize enough that Mars might be the only rocky planet other than Earth where we can actually directly study complex organic chemistry evolving through time.
You have 2 minutes.
Thanks. You can read the rest of the slides.
Okay, the next person up is Aaron. Go ahead. Barbara, you just go to the next one there. Barbara, same file, second page. Sorry, Aaron, this won't count towards your time.
No problem. While she's getting it, is the audio still good?
Yep, so here you're fine.
Good. Good deal. All right, while she's putting it up, I'll just introduce myself. My name is Aaron Engelhardt. I'm from the University of Minnesota. Our white paper sort of evolved from the meeting in Carlsbad, Mars Extant Life, What's Next? It was in late January and early February of this year. And the title of ours is, if we just got it up, Mars, the Representative Habitable World in Prebiotic Environment. And so the Carlsbad meeting was a group of people that were looking at, whether it was extinct or extant life on Mars, and there was a lot of people that were interested in subsurface life as well as, it's a kind of a contingent of prebiotic chemists. And so what came out of this meeting was a group of individuals. I'm listed here, Kendall Lynch from LPI is my co-lead. Some of the other authors are Penny Boston, Jen Blank, Alberto Ferren, Mary Beth Wilhelm, and Charity Phillips-Lander. We're interested in prebiotic chemistry on Mars and other bodies. Looks like it provides kind of a unique geochemical environment that could influence the emergence of life. I think that fits nicely with some of the changes that we saw in the goals document earlier, considering Mars as a prebiotic planet of other bodies. And I think that this also ties into some things that I think are going to be represented in some of the other white papers we'll hear about. And we're particularly interested in people that find these questions interesting in places where we could potentially find synergies. I think that some of the same planetary protection questions that were mentioned in the goals document, we're thinking about some of the same things. Planetary protection for prebiotic chemistry could look a lot, or at least have some overlap with planetary protection for extinct or extant life. I also think that the places where we could have overlap with other white papers, where we could potentially be co-signatories on each other, is that Prebiotic chemistry, I think, represents an attractive way to de-risk missions, whether it's sample return or otherwise. A mission that could be looking for extant or past life, many of the same chemical and analytical questions that we're trying to answer will apply with prebiotic chemistry as well. So you can look at our white paper or our one-pager for more information. That's linked from this meeting. But if these sound like interesting questions to you, we're eager to interact and see, potentially where we could have synergies for some of the other white papers. And if these sound like interesting questions to you in your own right, we have a Slack workspace where we're working together. There's still room for co-authors as well as co-signatories. So please do reach out if you'd like to talk. And thank you.
Perfect. Thank you very much. Bryony.
All right, so our white paper is titled The Evolution of Habitable Environments on Terrestrial Planets, Insights and Knowledge Gaps from Studying the Geologic Record of Mars. And so obviously habitable environments have been a major focus of the Mars exploration program over the last several decades, and we've done a fantastic job as a community documenting the range of habitable environments that existed on Mars, especially ancient Mars. But the purpose of this white paper is to make the case we need to take this question about habitable environments to the next big step. We're not done. The fact that we've documented these environments exist is great, but that we still have these huge outstanding knowledge gaps, and not just what the environments were, but also when they occurred, why they existed, and how they existed, right? So these 3 bullets I have here about how they evolved over time, the conditions they occurred under, and the effect of later processes on their record are all things we're just starting to understand, and we still really need to in order to tackle big questions about things like how habitable environments evolve on terrestrial planets more generally over time. And that's important not just for the early Earth, but also exoplanets. And it's also really important, too, these environments serve as a record for other Mars systems in their evolution, so things like the Martian interior, as well as the Martian climate. And so these environments are incredibly important, and we're going to make the case that we're not done studying them, that there's still these big things to do. So if you'd like to join up with us, please send me an email if you'd like to actually help with writing, or if you'd like to just be a co-signer, please follow the link to the Google form.
Good job. Thank you. Carol, you're up next.
Okay. The purpose of this white paper is to advocate for searching for extant life on Mars. The paper also springs from the recent workshop at Carlsbad, Life on Mars, What's Next? We will describe 4 types of environments on Mars that are illustrated in this slide that could host extant life, along with mission approaches for sampling them. So from the upper right, salts and evaporates are widespread on Mars and readily accessible at the surface with current rovers. Salts can host endoliths like those found in the Atacama, Chile, that obtain water from atmospheric humidity by deliquescence. In the upper right is ice. The recently published map shows that shallow ground ice is widespread on Mars, above 35 degrees north and 45 south. 1 to 2 meter depth drilling using currently available technology can access the ice to search for biosignatures produced during habitable periods in the ice. On the lower left shows caves and lava tubes. These can host warmer and wetter environments than the surface and can be accessed from surface openings. Biofilms that live on mineral resources in terrestrial caves are analogs to potential life on Mars. And then finally on the lower right, deep subsurface environments may host liquid water aquifers, and searching for them can be done with electromagnetic sounding. To actually sample them will require deep drilling. And I believe next slides our next presenter is going to talk about that in more detail.
Perfect. Thanks so much, Carol. All right, Vlada Stamenkovic is up next. And Vlada, you have 4 minutes because you have 2 and so you can yourself.
Damn, lucky me. I hope everybody can hear me well.
Yes, go ahead.
Okay, perfect. That was a great introduction. Hi, my name is Vlada Stamenkovic from JPL, and I'm just a point of contact for a large group of people that have been working the last 3 years quite intensively on actually something that we think is the next frontier of Mars and planetary exploration, which is a focus on what's happening beneath the feet of our rovers on the subsurface, with a focus on modern subsurface habitability. Now, we think that there's been a lot of data in the last 2 decades, more or less, that have been hinting that something is going on in the subsurface. We have a lot of discussions on methane variability, oxygen variability. We see how organics is being destroyed in near-surface environments. We have some hints on liquid water at depth, but those data are not really of the, still very confusing, still a lot of questions open, because we haven't really put the focus on actually answering the question whether there are modern habitats in the deep subsurface or shallow subsurface of Mars today. We know that today the Martian subsurface is one of the most promising, or one of the promising, as Carol said, habitats. We also have learned beautifully from MSL and the other exploration rovers that maybe even on early Mars, the subsurface has been actually a key habitat. And most of all, the Martian subsurface is literally, a Mars 2.0. It's a different planet. We haven't really, explored it so much so far. We've accessed sample in the orders of centimeters. We've sent some sounding, which was very inconclusive, but it's a completely unexplored world. And we want to address in 2 white papers. One is focused on the science, second one on technology and mission concepts. But the science paper mainly focuses on why is the science so interesting of exploring the Martian subsurface? How can we access traits of habitability with depth, locations where we can actually try to understand the habitability of the Martian subsurface, and the major science questions related to that. One thing that's really important is that these science questions are very strongly related to ocean world science and to RCU and human exploration. And we try to emphasize in this paper that exploring the Martian subsurface with a focus on modern subsurface habitability is not only the next frontier for Mars science, but also the next frontier for planetary science. And so in the next slide, please. We're going up there. Thank you. That is the second part, which is the second white paper, where we actually illustrate how are we going to do that. Now, there's been a lot of papers in the 90s saying, explicitly, the Martian subsurface and deep subsurface are super exciting. There might be key habitats today and in the past, but we don't have the tech to address those questions. Well, the 90s are some time ago, as I also noticed. And so there's been a lot of technological innovations, and we think that we're absolutely capable and ready in this decade to actually address those questions. Our key subsurface measurements that we want to focus on are separated in 2 goals: habitability versus life. We're following the approach, the wise approach of Curiosity and also Mars 2020, and we're going to mainly focus actually first on habitability, with a goal to address the availability of liquid water, whether there are energy nutrients at depth, and what happens to cells, cellular stability. How does the change of oxidants with depth affect cellular stability, availability of nutrients, and where do we have transitioning from environments which are segregated from the surface and can be self-sustaining? Now, we really want to try to go deep following the National Academy of Science recommendation, but we will not ignore the shallow. That's something really important and right there. One thing that's very important, we are aware that costs in the 20s will be quite limited because of Mars sample return. And so we've been exploring and will explore and lay out in this white paper all the classes that we can do, from small sats, small sats to new frontiers. And for more questions, please get back to us. And we're looking for everything from a wide spread of contributors. We've done a lot of work, but very happy about additional contributors and input. Thank you.
Excellent. Zachary Garvin, you're up next, number 7.
Great, thank you. So while we have a pretty good understanding now of the gas composition of the atmosphere of Mars, both at a global level and a more regional level, we are proposing that the next key and logical step is to actually perform gas flux measurements on the surface and subsurface of Mars. So this is incredibly important for determining rates of exchange of different gas species at the interface between the atmosphere and the subsurface of Mars, for getting a better understanding of gas cycling on the planet, and better characterizing these 2, broadly speaking, reservoirs of gases on Mars. Additionally, this also has important implications for whether gases could be supporting biological activity on Mars. So much like Earth, we're actually proposing, or it's a hypothesis, that there could be active, high-affinity trace gas oxidizing microbes in the subsurface actively participating in the gas cycling on Mars as we see on Earth, specifically by taking up reduced trace gas species at ambient atmospheric concentrations, species like carbon monoxide, hydrogen, and methane, where we already see some variability. and that could be being taken up by biological activity in the subsurface. So how would we actually go about measuring these gas fluxes? Well, we're proposing that we could use a soil chamber kind of design. These would be small dome-like structures that would be mobile, so they could be moved around by something like a rover on the surface of Mars, placed at various hot spots where we expect flux to be highest, or at least would have contrasting variability in fluxes. So what we would do is lower these down onto the surface. It would isolate a small portion of the regolith as well as the surrounding atmosphere of that isolated region on the surface, connect that to gas detection instrumentation, and then allow the gases to be detected over time, whether that be a short period of time like daily or hourly cycles, or longer periods of time, longer experiments like seasonal cycles, and detect change in gas composition over that period of time. And so this would allow us to, that allows us to calculate rates and understand cycles. So feel free to email me for more questions. Thanks.
Thank you. Charity Phillips-Lander is up next with number 8.
Hi, I'm representing the MEPAG science team. So MEPAG, the Mars Astrobiological Cave and Internal Habitability Explorer focuses on 2 goals. First, have habitable conditions ever existed in a Martian lava tube cave. And we specifically want to target, as you can see up in the upper left-hand corner, caves that have been modeled to contain metastable water ice today. Our second objective would be, or goal would be to determine whether or not life arose or migrated into a lava tube. And so to achieve these goals, we're going to look at the nutrients and energy available in lava tubes, the evidence of past aqueous alteration, presence of presence of water ice today, and then biosignatures and evidence of life. We're considering several mission architectures, and that includes the actual rover. We're also considering technology developments, and those will be outlined in our white paper, that'll help enable doing this within a New Frontiers cost box. And then we've also started looking at the instruments that are available to achieve these mission objectives. We're currently seeking additional co-authors who can contribute to any of the areas you see on this slide, as well as co-signers who wish to support our mission concept.
Excellent. Thank you very much. David Blake, you have 9 and 10, so I'll interrupt you at 4 minutes.
Okay, thank you. Can you hear me okay?
You're fine. Go ahead.
Okay, so I'm kind of an instrument guy, so the next couple of talks are going to be on instruments we're working on. First is MEPAG. So compositional heterogeneity at a fine scale can reveal evidence of present or past habitability, minerals and biosignatures. MEPAG is an ARM-based instrument that will identify these features on Mars. It's designed to use curium-244, just like the APX instrument on Mars Science Laboratory. It's got a 2.5 centimeter field of view with about 100 microns resolution. No moving parts. The instrument's just pressed onto the surface and held there for the analysis. Depth of field of about 1 centimeter as a result of the kind of X-ray lens we're using. Detects elements sodium to bromine and quantifies them at the 0.1% level in less than 3 hours. It's a native full-frame imager. It collects an image every 0.3 of a second, and optimally in 10,000 frames, you get a full image. You can see in MEPAG's data set there. Basically, you get elemental maps, regions of interest, which are chosen by the instrument using an unsupervised machine learning program, and quantifiable X-ray fluorescence spectra from each ROI. In principle, solid materials can be characterized with just 3 measurements. The first is structure, crystalline structure. Second is composition, or elemental content. The third is morphology. MEPAG has the potential to determine all 3, as for example, when an ROI composition can be used to predict a mineral species. So that's it.
Did you do both of your slides, sorry?
I'll start now there's another slide. Yeah, okay, this one is CheminX. So I'd like to describe a next generation CheminX RDXRF instrument. So for Chemin on MSL, all the raw data, refinement results, open access papers can be found on the website shown in red there. They're all downloadable. To remind you of what Chemin does, it identifies all minerals present greater than 1%, quantifies all minerals present greater than 3%, determines the abundance of all major elements present in each mineral, hydrogen above, determines the valence state of all elements, including speciation of multivalent elements like iron, quantifies the abundance of the amorphous components. And now I want to talk a bit about CheminX. What are the improvements? It does what Chemin does, but it's half the mass, 1/3 the volume, and utilizes 1/10 the energy of Chemin. Analysis times are 15 minutes to 1 hour. We have an incorporated silicon drift diode, so we collect our own overall fluorescence data. And the bottom line is the result is that we can take a Chemin instrument and deploy it on a Mer-class rover with the addition of a powdering drill. And I guess that's it.
Excellent. Since we've got a little bit of time, just clarification for a white paper. What about an instrument? Like, do you envision writing it about just the instrument and its design, or focusing on the science questions it can address, or?
Well, it would basically be the science questions, and the science questions that could be answered with the instrument.
Okay, thank you. And Anna,
Sure.
You're up with number 11.
Yeah, hi. My slide. Perfect, thank you. So we would like to use the opportunity of writing this white paper to talk about basically our current understanding of Mars magnetism and the ancient dynamo field. And we would also like to bring up some science opportunities that would really enhance our current understanding of this topic. And was really some of the first order outstanding questions addressed things like the Martian crustal, the nature of the Martian crustal remnant magnetism, as well as processes that would lead to these sort of signatures that we observe, and then of course the characteristics of the Martian dynamo. And really our current understanding is based on a range of different data sets that of course come with limitations, and these include for example, resolution issues that are associated with our orbital data sets, but then also issues like missing geological context or just sparse sampling when it comes to data sets like looking at meteorites or our one surface point that we have with InSight. And therefore, we would like to bring up some recommendations that would really benefit us in our understanding of the magnetic field, and these include, well, first of all, aerial platforms, so really using drones or long-lived balloons to get at these low altitude and high resolution measurements of the magnetic field. And we would also like to discuss Mars sample return, so really start thinking about what kind of aspects would help us understanding the magnetic field from a polymagnetic perspective, having this opportunity coming up. And you're welcome to contact me if you want to be involved. We're very open for contributions from other people. Thank you.
Very good. And thank you to all of the speakers during this session for pretty much staying on time. We are now in the discussion period, so if people have questions or comments for anyone who had spoken, clarification questions, feel free to put them in the chat. Additionally, from a higher level view, are there any areas that appear to be missing in the areas of astrobiology and subsurface investigation? And just to check, Eileen, are you back on?
I'm on, yes.
You are on. Okay, cool. See lots of people typing, but questions aren't appearing yet.
Yeah, this is Eileen. I'll just use the mic. If Bryony is still out there, can you summarize in about 3 sentences what you think the biggest knowledge gaps are for habitable environments?
Sure. So I think timing is a huge problem. I think it's something we really don't understand is when these things occurred, and that's a bigger problem on Mars in general, right? But that's something that's a big problem if we want to understand why things are habitable. I think we also would like to understand what conditions they occurred under, and so that's things like particularly climate, right? So what conditions lead to climate habitable environments. And then I think a big one is sort of where do the fluids come from, and what is their chemistry and things like that. So I think those are 3 big ones I would identify. The 3 bullet points I had in my slide are actually a pretty good summary, I would say, or something along those lines.
Great, thanks.
Great. And we had, actually, Bryony, we had a question from Jeff Johnson. Do you anticipate discussing chemiostratigraphy and aqueous alteration?
Yes, definitely. So if you'd like to contribute to that discussion, we would love to have you on board.
Perfect. For Garvin, Zachary Garvin, Claire Newman points out that trace gas measurements would also be of great use for atmospheric modelers, hoping to understand the water cycle and the importance of the regolith. So is that an area that you'd be interested in exploring, Zachary?
Certainly, yes. The idea is not at all limited to astrobiology. It's just gas cycling and general atmosphere modeling and climate in general, but many implications for trace gas measurements.
Excellent. Barbara, I appreciate the slides, but could you actually put up the agenda with the white papers on the second page of the agenda? Then people can see who all spoke. Rich Zurich had asked Carol, how would you detect life? I feel like that's maybe getting into details, but a brief answer.
Yeah, so the answer is, in terms of the paper, in the workshop there was a subgroup that looked at life detection technologies, but one of the things that I would like to advocate in this paper is that more funding gets put into the development of life detection instruments. It's an area that has been underfunded for many decades.
Excellent. Thank you. Tim McConaughey. Sorry, Tim. Eventually I'm going to get your name right. I'd like to hear more about abiotic processes that might be addressed or need to be addressed as part of the trace gas consumption experiment. For example, water vapor exchange and oxygen chemistry.
Yes, so again, certainly the idea of measuring trace gases has a lot of implications other than just biology, and certainly reaches into abiotic processes as well. The great thing about a chamber design also is that you can have other types of probes that are measuring different conditions, including moisture content and things like that. And you could even have isotopic measurements occurring as well, which would help with abiotic processes. But if you also have more ideas about what could be done there, of course, we're looking for any and all input and expertise in this area. So, thank you.
Great, thank you. Question for Anna from William Rapine. Do you plan to focus on science or give a large path to possible solutions like mission concepts?
Hi. So no, I think we're really planning on focusing on the science itself, and we would really like to motivate why these sort of measurements or these sort of recommendations that we're bringing up, why these are so important to enhance our understanding, and then pointing at other white papers, such as the one that by Jonathan Babs and his group, they're going to present later on about like a helicopter technology. So for us, it's more like the motivation. We really need those measurements. If that makes sense.
Yes, thank you. David Blake, there was a question from Liz Ramp. Would you also discuss how ChemNex could be used on planetary missions on bodies other than Mars?
Yeah, sure. So I'm writing a white paper for Venus landed mission, and we're
We're kind of spec'd into a flagship mission to Venus, and I'm also writing an overall white paper for solid solar system objects for XRD, XRF.
Excellent, thank you. And I saw you put that in the chat as well. Thanks. So we had a couple comments about kind of a higher level look from Jim Kaufman and Michael. I echoed it. Some of these concepts are calling for new frontiers level missions, such as MEPAG. Do people feel that a Mars New Frontiers mission could be selected as long as MSR is being implemented? And it's pointed out the next opportunity for a Mars mission to be added to New Frontiers is in 2027. I think this is a little bit outside white papers in particular, but Eileen, do you want to talk about that at all?
I can certainly give my opinion. Yeah, given a New Frontiers mission candidate list defined by the upcoming Decadal Survey Committee, my opinion is, based on everything I've heard here and everything I continue to hear, that there's high priority science for Mars that can only be addressed through a New Frontiers category of mission. And my opinion is that the Mars program being able to strategically work in other areas doesn't negate the need to strategically work in this area as well. This, in my opinion, is a toggle that we should be allowed to throw if the science calls for it.
Excellent, thank you. So people in general, if you do have a kind of a New Frontiers class mission concepts, definitely it's important to get white papers in on these.
But I do think, yeah, I just want to make sure that it's clear that it's the science that needs to drive the mission rather than, hey, I've got this concept and I can only afford, right, because of X, Y, or Z. The science has to be New Frontiers class. Does that make sense?
Yeah, that's an excellent point. As you and I have talked about before, New Frontiers doesn't just mean in a certain cost class, it means high priority on a planetary science framework. Okay, I'm skimming through these. We had a question for Bryony from Andy Seja. Are you planning to include the search for evidence of ancient life in your white paper in addition to the search for habitable environments?
We could certainly consider that. I think that could also be a great separate white paper, but that's something I'd be happy to discuss.
Excellent. And Jesse Tarnas asked for Vlada. Can you outline what budget or payload trade-offs you would expect for subsurface exploration missions? So this
That's a great
scale, but a brief answer.
Yes, we're looking at trade-offs from sub-discovery class small spacecraft with delivering payload to the surface for understanding liquid water in the ground and trace gas sniffing, to New Frontiers capabilities, which include also drills with drills that already exist, have been tested and validated to depths of 100 meters and plus on the Earth.
Excellent. Just to add on to the New Frontiers focus discussion that we just had, it's pointed out that with New Frontiers 6, we'd be talking about a launch date in the early 30s, which in theory should be post-MSR anyway. And Michael Mishna points out that for New Frontiers 6, we really need to be advocating for important Mars science of New Frontiers class in the upcoming Decadal survey. I think that's all that's coming in. If I missed your question, sorry, type it in, retype it in. Question from Bryony. Oh, this is just,
responding.
Yep, thank you. So Andy, see the chat. So it seems like that's it for this session. I'll just throw out there as food for thought as we get around to the final discussion period where we can kind of revisit again the question of what's missing. I do not work in astrobiology. I don't work in any of these areas. But looking at it in the fields of astrobiology and habitability, I thought it was interesting to see which parts of Mars were being explored. So we had subsurface, we have ice, we have things looking at trace gases and all of that. I think that's another thing to think about. Is there a aspect of those types of investigations that is not being covered? Then again, we do have Mars sample return as well. So perhaps everything is covered between all of these avenues. But keep that in mind, and we can revisit that if anyone does see something that perhaps is missing. Eileen, should we take a break?
Well, let's go ahead and take a break. I think we all need to shake it out a little bit. Thanks very much to all of the speakers. Really, really interesting and good discussion. And we will come back at 10:25 a.m. Pacific time, 1:25 a.m. Eastern time.